Yes, we were talking about DL and R. So DL, L is length, R is distance, so length is also distance. In this case, their extremely small amounts like DL and DR is the same. Yes, DL and DR is the same, even if they don't have the same length. Because, in my question, R is changing parameter, R continuously changing. So there is no fixed value for R, but L is fixed. It doesn't matter. Their limiting form, DL means point, DR means point. So DL and DR is the same size of a point. Also same physical quantity. So it doesn't matter if you write here DL or DR, KQL from B to the L plus B, dr over R square. So you can change it and write R. Now, if I evaluate this integral, KQL minus 1 over R, changing from L plus B to the B to the L plus B. First, I will substitute, definite integral. So first we substitute in function upper border, upper value and lower value. So electric fields, we can bring this K if you want in front of negative in front of K, or you can keep in parentheses, no problem. KQL minus 1 over L plus B minus another minus 1 over B. So this minus, the second minus is subtraction. First and last minus are come from function. Finally, I have this function KQL 1 over B minus 1 over L plus B. Here is the electric field. Be careful. If you open this parenthesis, still we have inverse square law. KQLB minus KQ L plus B. Look at this function KQ R square. So R square already exists, but there are two distances multiplied, L and B. So finally, form is the same form. Electric fields obeys inverse square law. So downstairs we have square of the distance. Square of the distance is kept. Also in the second term, KQ over square of the distance. L is a distance, L plus B is the another distance. So find as a dimension, KQ L square. Downstairs in each function we have distance square. Okay. Yes, this is the general form. So for any amount of charge in the cable, any distance B, any length of L, you can calculate electric field. Okay. Now, another example, ring. Today's last example is charged ring. Electric field of a charged ring. So ring has symmetry higher than cable. So cable has a symmetry. As you see, we calculate electric field as you see on the symmetry axis. Where is the symmetry axis? This is the symmetry axis passing through center of the cable. So I calculate only electric field on symmetry axis. But if I move this point from symmetry above from the symmetry axis, for example, any point in XY plane, I cannot calculate electric field using analytic methods. So I am choosing specific points on the symmetry axis of the system. Okay. Yes, same for ring. So I have a charged ring, lies on horizontal plane, and I want to calculate its electric field according to symmetry axis. So any point on the symmetry axis. So this is my ring. You know what is ring, charged ring. The radius of the ring is r. R. So this is horizontal. I won't write x, y, z, but maybe this can be x, this can be y. It doesn't matter, but I will only write here vertical, horizontal, horizontal axes. I won't label x, y, z. Okay, horizontal. Two horizontal axes and one vertical axis. So my ring lies on horizontal plane, and vertically I can show symmetry axis. I can only calculate electric field on symmetry axis. Also, in the previous example, I did this calculation on symmetry axis. Symmetry axis. Okay, this is also symmetry axis. So, analytic method works only for symmetry axis. Otherwise, it's not possible to use analytic methods or calculate electric field. It's not possible, not easy. And there is no analytic solution. We have only analytic solution if we check cable electric field in symmetry axis. Also, rings electric field on symmetry axis. Away from the symmetry axis, I have no solution. I have no analytic solution. Numerically, maybe numerically I can calculate something, but I think the error will be higher if I move from symmetry axis. Okay. Now let's choose a point on the symmetry axis. This point. So it's distance from origin. So let's say this is the vertical and I say z. Z is the distance from origin to the point I want to measure electric field, calculate electric field. So question is calculate electric field Z above from origin. Okay. Yes. So ring, if you compare with line, more symmetric system and its calculation more easy because of symmetry. Now I am using the same procedure. First, I am choosing a dq. I will show its electric field vector, then integrate. Let's see, dq is this one, dq. Let's say dq1. dq1. The distance from origin is r, radius. As you see, if you rotate dq on this ring, r is not changing. Also, if you rotate this dq on the ring, vertical direction z is not changing because dq lies on horizontal plane. So horizontal distance doesn't change in vertical distance, sorry. Vertical distances doesn't change in vertical axis. Also, radius is not changing. Now that makes easy my calculation. Let me show its electric field vector. So I have to show this electric field vector. So dq is here. I want to calculate electric field at that green point. So electric field is attractive, repulsive. So it repels 1 coulomb, you know. I want to calculate electric field. So dq is positive. Electric field vector is repulsive. So it repels this point outward direction. Let's say E1. Yes, E1. This angle alpha and this angle alpha, or this angle alpha and this angle alpha is the same. Okay, same angle alpha. Now, because I have a ring, let's find its symmetric one. Which charge is symmetric about this axis? So another symmetric charge is on the other side, on minus x-axis. On the left side, let's say. This one, dq2. So dq2 also is at the same distance. Look at the triangles. So because of symmetry, we have same triangle. In this case, this red electric field vector is E2. So E1 and E2 same in magnitudes. They are in the same magnitude. Okay, so the size of electric field 1 is the same as size of electric field 2. Let's write K dq over, what is the distance? This is z, the distance z. Let me show again. This is distance z. Distance z. So r is the horizontal one side, horizontal side. Z is the vertical side. So r square, z square. So square root r square, z square. Same for each charge and distance in each side is the same. So I am taking the square of square root r square, z square. Yes. Now I get two couple of charges. So I can show infinite number of couple of charges around this ring. So this is an example. You can choose also another couple of charge. One is the one semicircle, other charge on the other semicircle. Their combination gives this kind of shape. So what if I sum? These are magnitude, but what if I sum two vector? E1 as a vector sum E2 gives us k dq. So E1, let me write only E1. So E1, as you see, E1 has horizontal and vertical components. I will write now E1 horizontal. I won't say X or Y, horizontal. Because when I change this couple of charge and rotate, the components are changing. So I say E1 horizontal. Horizontal component of E1 given by K dq over r square z square. So I should multiply by cosine alpha. That's the horizontal component. Negative leftward direction, let's say leftward direction. E1 vertical given by sine alpha. So k dq r square z square sine alpha. Same for E2. Horizontal component given by cosine alpha, vertical component given by sine alpha, but we have a difference. As you see, when I sum horizontal component of each vector, they cancel each other. So yes, E2 also horizontal is minus of E1 horizontal. I can write this one because they are always in opposite direction. But E2 vertical is the same as E1 vertical. So there is no problem in summation in vertical vectors. You can directly sum in the same direction. But horizontal components, if you choose any couple of charge, but it should be symmetric. In this case, E1 plus E2 gives us E1 plus E2 gives us this solution K dq over r square z square sine alpha plus K dq r square z square sine alpha. Same, so it repeats. I repeat it. Same contribution comes from E1, same contribution comes from E2. So if I keep adding another couple of charge, another couple of charge, another couple of charge, because I can show all couple of charges has the same contribution. For example, this is my ring. Let me show in the figure. So this is my ring. This is my ring. So I choose this couple of charges, but there are infinite number of couple of charge. First couple are these are another couple yellow, another couple red. One charge is one semicircle, other is in another semicircle. As you see, these are in couple and symmetric also. Green one. One is one semicircle, other is another semicircle. So as you see, if you collect all these couples like E1, E2, E3, E4, E4, E5, E6, E7, E8, En minus 1. So all these couples, E1 plus E2 is a couple of charge plus, let's say, E3 and E4, another couple of charge, another couple of charge, another couple of charge, En minus 1 plus En. These are couple of charges. And each couple of charge gives the same result, same contribution. So that means I have n times this term, n times this term. So I'm integrating actually all these terms. So k r square z square sine alpha exist in all term. I'm only adding dq, dq, dq plus dq. What is the result? Result, this is the total charge of the ring. Q ring. So answer is k q ring sine alpha over r square z square. Okay? So it's very more easy, more simple. You don't need to write an integral because each couple of charge, one couple of charge, two charges, one couple. One couple of charge, there are two charges. Each charge contribution to the total electric field same. Same distance, same vertical distance, same horizontal distance, same hypotenuse, same angle alpha. In this case, I sum all terms, but each term is the same. That means dq plus dq plus dq plus dq gives you total charge. Now, what is sine alpha? If I look at this figure, I can write sine alpha from the triangle. As you see, sine function, vertical distance z divided by hypotenuse square root r square z square. So if I substitute sine alpha is z over root r square z square, then electric field of the ring is given by kq ring z over so r square z square and square root r square z square. Let's simplify kq ring z over r square z square to the power 1.5. Yes, that's the ring's electric fields at a distance z above from the center. Above from the center. Okay? Yes. Now I get this solution. Let's make some conclusion on this solution. Conclude my solution. So I have this ring and I can calculate only on symmetry axis z above from the ground, this is not ground, z above from the origin. Yes, I know electric fields. If the charge is q on the ring, I know electric fields. at z above from the center is k q z over r square z square to power 3 over 2. Now let's find limit of the function. Limit. What is the limit? When the z distance, because this is z dependent, r is not changing, k is not changing, q is not changing. I'm changing z. So z is the distance. So what is the minimum z and maximum z? Let's see the limit. Limit means minimum and maximum values. Sorry, z. Z equals 0 is the center. Z equals 0 is the center. What is the electric field at the center? Let's see. Electric field at the center means that choose 0, Z equals 0. In this case, there is no electric field at the center. So my function, my solution tells us there is no electric field at the center. This is theoretical conclusion. Theoretically, mathematically, we calculate. What about physical meaning? So why physically, let's prove it. Why electric field at the center is 0? We can prove using our physics knowledge. We know vector electric field is a vector. So if I choose this couple of charge, their electric field at the center cancels each other. This electric field E, this electric field E, they cancels each other because of distance r. Another couple of charge, this charge electric field and this charge electric field in opposite direction cancels each other, so on. So if you choose any couple of charge, they cancel their electric field because of one full circle. So there is no electric field at the center. This is the physical meaning. Another limit at infinity. Limits, what if we are at infinity? Z approaching to the infinity. Approach. In this case, k, q, z over r square, z square to power equal. Approach. It's approaching, not equal, approaching. K, Q infinity over. So if the Z goes to infinity and Z square, infinity square, R square is negligible. So what does it mean? Upstairs in this fraction, slower than downstairs. So downstairs, when downstairs reach to the infinity, theoretically, upstairs still as a number is a number. So the system is approaching to the 0. Another 0 when electric field measured at infinity. Experimentally, not infinite, experimentally far away from the center. For example, I have a charged ring on my table. I measure 1 kilometer away from the ring. Of course, you cannot measure any electric field. For example, sun creates also, so sun creates light. So release the light, emits the light. So light also carries electric field and magnetic field. Sun shine, Earth, also other planets. But for Andromeda galaxy or another away from the solar system, sun cannot shine it. So this is Andromeda galaxy for the sun at infinite distance. Okay, so that means there is some experimentally fine some all these physical quantities are has a finite value. So there is no infinitely large charges, infinitely large electric field, or at infinite distance still non-zero physical quantities. These are impossible. So electric field is getting weaker, 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 then drop to 0. You don't need to go to the infinity. Before you go to the infinity, experimentally, it's already 0. Okay? Yes. Now, it's 0. In the beginning, 0. Finally, 0. if I plot this graph, electric field versus Z, what kind of shape I have? Let's discuss electric field behavior of the ring starting from origin to the infinity. So at origin, I know at origin electric field is 0. At infinity, again 0. But between 0 and origin and infinity, at that short distances, electric field is not 0. It's positive. So there is some Z, R, Q, K. So it's positive, not 0. That means between center and infinity, in this region, in the graph, I should put some data positive. In this case, I start from 0. I should start from 0 and rise. But finally, I should go back to the 0. So that means I should pass some maximum. Otherwise, it's impossible. Impossible to go down. So it should start from 0, yes. But it should rise because when I leave the 0, electric field becomes positive. So it's rising, but at some critical point reach to the maximum, then start to decrease because at infinity it should go back to 0 again. So question is, what is this maximum electric field? Yes, this is your homework. Find at what distance electric field is maximum. Write your solution according to R. At what R? So Z as a function of R, okay? At 1 R, at half R, at 3 R. Find it. At what distance? Okay? At what distance electric field is maximum? Do you have an idea how to calculate? Do you have any idea how to calculate this maximum electric field? Which methods, mathematical methods, gives us maximum? Optimization problem. Maximize. Maximizing function. Minimizing. How to find maximum? So if you pass physics, not physics, calculus lectures, course, and if you are successful, you should know that. So your calculus teachers teach you finding maximum. If you take the derivative of this function versus z, that means dE over dz is 0 at a specific distance, z. So what is this z? At what z? It satisfies this condition. So that's satisfied. So z equal, let's say this is the z0 at z0. So this is 0 at z0. dE over dz when z equals z0 is 0. Yes, find z0. At what distance z0 electric field is maximum? Its derivative at that point gives 0. Okay.